Okay, hello, welcome back, my dynamic friends. So let me quickly recap what we have been looking at so far. We are looking at the kinematics of a particle, and we looked at two different frames we can describe the motion in. One was rectangular frame, and the other one we have studied so far was tangential normal frame. Rectangular frame was suitable for problems when we had this separation of different aspects of motion along separate axes. A good example was a projectile motion when we knew we have acceleration only in one direction, in the vertical direction, and there was no acceleration in any other direction. So this separation between different axes was well suited for rectangular frame. We also looked at tangential normal when we had good information about the path of the particle. We could define the frame according to two directions, tangent to the path and normal to the path, and based on these information and adding the information about the path, we could define velocities and acceleration in a meaningful way that is related to the path information. So these were the two ways. In this video, in this and next few videos, we look at the third one and the last one we study here, and that is polar frame. So rectangular frame, when we had rectangularity or separation along axes, tangential normal when we have good information about frame. What about polar? Polar, in my opinion, is very useful when you have a strong rotational aspect in the motion. And let me give you an example what I mean by that. Assume you have a path and you have a bunch of soda cans that are moving along this rail, and you have a lever, maybe draw it with red, that comes and lever turns and pushes these cans along the path. So this rotational aspect makes this problem well suited for defining the motion in a rotational domain. Often when we are talking about polar frame, we have some information about the path, but the more important thing we care about is this rotational aspect. That's what makes the problem well suited for polar frame. Okay, so let's be systematic and, like before, first define a set of coordinate frame in a meaningful way. So let's pretend we have some arbitrary path, a particle. This path could be arbitrary and we may or may not even know it, but I just draw it for the purpose of showing it. And there is a good point in a space that things are rotating about that. A good example was this hinge joint for the lever that was fixed. The lever was turning around that. If we have that kind of point, that can be our origin. So origin, we define it as a good point that things are rotating about. When we have that, we have already made significant progress. We can now go ahead and define our first axis, call it UR. This is radial axis. And it is in the direction that points from the origin to the location of the particle. So one thing you can immediately note here as the particle moves to a different location, radial axis turns. So it is similar to tangential normal frame, a moving and rotating frame that becomes important when we study the velocities and acceleration. The second one, okay, that is the first axis. We need to define the second one. Obviously, we like to find the second vector to be perpendicular at least to the first one. So that would be somewhere along this axis. And we take the positive direction, let's call it u theta, in the direction that our angle is increasing. That's an ugly theta. So if this is theta, if we consider this direction to be the positive direction of rotational direction, we take the transverse axis to be in the direction pointing towards increasing theta. So let me add this. In this particular case, u theta would be here. These are perpendicular and in the direction of increasing theta. So that's how we define the frame itself. Let's actually, now that I have a lot of space, do I go here? Yeah, maybe, why not? Oh, actually I've talked a lot. Let's stop it here. So now we have fully defined the frame. We are ready to go and define positions, velocities, and acceleration. That will be the next videos. So I'll see you there.